All right, physics 1101. This will be lecture chapter 3A lecture. And this will be, we're going to skip the first part. I'm going to go back to that later, but I'm going to do sort of a continuation of chapter 2. This will be on projectile motion. And this will be, part of this will be on the first exam. And then I'll be doing this again, and then we'll be moving in for chapter 3 on vectors and relative motion. So we'll do that next. So this will be on projectile motion and this is section 3.5 and 6 in the tab, but this is primarily just 3.5 and 3.6 as far as that's concerned. So what we're going to cover here is just two types of motion as far as projectile motion. One type will be where we launch a ball or something and it lands at the same height. So this is exactly like we did in lab 2 with the FET program. So we launch it and it goes a certain range. Now what we find here with any kind of projectile motion, and there's a couple pictures here in the text as far as that's concerned, and we'll do more of this. So what we have here is projectile motion. If you look at the basketball shot we did, and we'll also do this one here, if we see projectile motion follows a parabola. So the shape of this graph, where we have x is in this direction and y in this direction, this is a parabola where y is proportional to some x squared as far as that. So that's the shape of, you would actually see that. When you shoot a basketball, that is what you see there. Now this is a little different from what we had in chapter 2, and I'll get to that, all right, in chapter 2, we're dealing only in motion in either x direction or y direction. So we plot there x versus t, all right? We see a graph, a parabola for that, where x is related to, x is x naught plus 1/2 at squared, where a is the acceleration. So when we have acceleration, then we have a parabola as far as that's concerned. Similarly, when we have an object in free fall, all right, where y is 1/2 gt squared, now what we'll see there is it does this sort of thing, where it goes more and more negative, where we start off at 0 and it becomes more and more negative because g is approximately minus 10 meters per second squared. So the shape of this graph is y is minus 5t squared. So it becomes more and more negative, but this is still a parabola. All right, so these are parabolas, but we're plotting position versus time and y versus time here. All right, so you can't actually see that. I mean, if you look at it actually, what you're going to see is something, a video of, say, a car getting faster and faster and faster. It's still moving in one line, but when we plot position versus time, it accelerates. So when we plot velocity versus time, it's a straight line. Same thing here, plot velocity in the y direction versus time, and it's this kind of motion. more and more negative. All right, so this is what we had from chapter 2 to review, but in chapter 3, we're actually going to use the fact that normally in the x direction there's no force on it, but in the y direction we always have gravity acting on it. So that's the distinguish here in chapter 3. So with projectile motion, and I will move on a little bit from here. So let's look at this type of motion that we see, and let's just stick with that again. So if you launch a ball and it lands the same height, so this is x, or we can also use this as the range, r, comes back to the same height. So this is not like kicking a ball, because when you kick a ball, you're a certain height up and it lands, or kicking it through a field goal, right? That's covered in the text, but we're not going to be doing that. In that case, what you have there is you kick it and you're trying to make it over a goal a certain height up. So this is a far more complicated part of the problem. We're not going to be doing that. We're only going to be looking at something where it's launched from one height and lands at the same height, right? So in this case, we have factors involved. We have theta, which is the angle it's kicked at. This, you can see that from the lab too. And we have a speed that is launched at, v there. Now it actually would have a component v sub x and a component v sub y. We'll get to that as far as vectors, but we're actually having a speed v naught launched at an angle theta above the horizon. All right? So it's then going to go a distance x we'll call r. And that depends on the speed and the angle. All right? Obviously, if you just shoot it straight across, it's not going to go anywhere. If you shoot it straight up, it's not going to go anywhere. So what is that expression? How do we get to there? It depends on a couple things. First of all, we're assuming no air resistance. No air resistance. So we have the acceleration. So the only acceleration we have is a in the y direction, which is given by g. Okay? In the x direction, that's 0. So we have a constant. So we're given, so in the x direction, v in the x direction is constant, right? So the only thing you want to see, it's going to go up. And we can do that if we look at the individual components, is what you do with what we call the basketball program, basketball shot. We look at both the x and the y, and there. But for this part, we're only going to be dealing with, we call the range. So the range, so it depends on the speed, and it depends on the angle. So assuming no acceleration in the x direction, no air resistance. So how was that turn out to be? Well, it turns out, if we calculate this, the range will be given by v naught squared times sine of 2 theta, and this will be in degrees, over g. All right? So that's what the speed is. So that's what we have there. All right? So let's do an example related to this, and then we'll look at okay. So let's do it. So let's pick V naught is 10 meters per second. Let's make it 20 meters per second. Theta, say, is 15 degrees. All right? G, just for simplicity, I'm going to pick 10 meters per second squared. I'm only going to use the absolute value of this because the range, what we have here is G, we're using positive, and V naught is squared is positive. So what would be the range for this problem, right? I'm only going to use 10 meters per second squared, just for simplicity, since I don't have a calculator at the moment. That doesn't matter. So anyway, put that in. So that'd be 20 squared times the sine of 2 times 15, which is 30, over 10, which is 400. Sine of 30 is 0.5 divided by 10. So that'd be 200. That would be 20 meters. All right? Okay, so that's what we have there. Now, if you look at this, so this is the factor we V naught. But one thing with we see the angle is sine of 2 theta can range from effectively 0 up to a maximum of 1, right? You can't have, once it gets beyond that, it goes back. You only take, so it can be as small as 0. That would be if we had 0. Right? And if we pick 90 degrees, that would also be 0, because sine of 0 is 0, and the sine of 180 degrees is 0. So if you launch it directly here, sine could go anywhere. If we let it drop it directly up, sine could go anywhere. Now if you look at this, what's the farthest this thing could go? Well, the biggest sine theta can be is 1. Largest can be is 1. And that occurs when we have sine of 90 degrees. Gives you 1. Well, what's 2 theta? 2 theta is 90. Theta would be 45 degrees. So that's, assuming no air resistance, the farthest it could possibly go is with angle of 45 degrees, which may seem a little contrary. There are other things that contribute to this. In reality, you have air resistance. So if you throw in, say, a javelin, all right, there's the dynamics of the javelin make it so it's about 30 degrees. A golf ball, again, based on the dynamics, based on the way it has dimples, and using the spin of the ball, it's a very small angle, which actually contributes to keeping it up in the air. The air resistance, the airflow around it actually keeps it longer than would be otherwise. So that's what we have here. Now, what we're going to see is as a maximum of, at 45 degrees, the range, but then it gets smaller again. And so at 0 and 90 are the same. So 0 and 90, 0 degrees and 90 degrees is 0. But what we also find is that if we try this angle, so if we have theta, we get a range. If we also do 90 minus theta, let's see what that turns out to be. So 90 minus theta. All right, so that would be, instead of 15 degrees, I shoot at altitude 40, not 75 degrees. We do this exactly in the lab. So that would be 2 times 75, which would be the sine of, let's do this again. So that'd be 400 times the sine of 150 degrees, which is 0.5, so that's 400 times 0.5, which would be equal to 20 meters. So 75, so sine 90 minus 15, 75 degrees, it goes the same distance. All right, so one case it goes like this, the other case goes up and comes back the same way. So both angles give you the same range, and you should see this in lab 3. Okay, lab 2. So that's the first part of that, the range problem. One other thing I'm going to look at here, and we'll see this, is applications. We look at range projectiles. We notice above this part here, right, where we drop a ball and shoot it out horizontally at the same moment, they both will land at the same time. Right, so we have the range problem, range forming problem here. So that's what we have there. So let's move on to the second part of projectiles. Again, we're keeping it somewhat simple here. So we have the problem. So we drop it, right? Takes a certain amount of time to fall, say t. We shoot it out at the same moment. Give it some V naught. This is horizontal. It will land at the same time, right? They will both land at the same time, because what we see here, we have only gravity acting on, so the acceleration, which is g, which in this case, minus 10 meters per second squared, roughly. You can use minus 9.8 to be exact. So it falls the same time. All right, so they'll land at the same time. As long as it's shot, it doesn't matter how fast it shoots, because it goes farther, but gravity's still acting on it. Now, part of this, people get this misconception that if you are walking and drop something, say you drop something right in front of you, all right? So say I'm walking and I drop this, I'm not going to do it here. The perception is that it will fall straight down as you keep moving on. So as you move on, it falls backwards, sort of. So when you let go of it, the perception is, oh, there's no gravity acting on. There's nothing acting, no force acting on, it just falls straight down. That's not what happens. What happens is, if you walk, it stays long, it should land right next to you, not back behind you. This is because, you know, neglecting air resistance, it has initial speed as you let go of it, and it will keep going as it falls. Now, some common misperceptions, if you ever watch, you know, World War II war movies where they drop a bomb out of a plane, right? So they're going a certain speed, say 100 meters per second, and they drop a bomb out of the plane. Well, if you look at the camera from inside the bomb bay doors, the bomb appears to be going straight down, because that's what it is, going straight down relative to the plane. But it's not literally going straight down, it's still going along. So what's happening is, it's not, you know, if you look straight down, if you want to drop a bomb on a target straight down, that's not going to go anywhere, because what happens is it's going to go at the same speed. So, depending on what it is, say it takes 10 seconds for it to fall, all right? You have initial speed of 100 meters per second. It's going to take 10 seconds to fall. The distance falls x, to fall horizontally, is velocity times time, which will be 100 times 10. It'll fall 1,000 meters ahead of that, all right? this is why, so it's not going to land anywhere near. And if you're dropping a plane and dropping a bomb from 25,000 feet like they did in World War II, you're not going to have any result at all. So this is why the complicated bomb sights were such that, all right, you want to land on this target, all right, you need to control the speed and based on your height, when exactly to launch to land on a target in front of. So that was the Norman bomb sight, which is actually a big secret. And to be able to land accurately bombs from almost 5 miles up. So that's what it actually does in that case, all right? So we'll be looking at, so let me do another example related to this. And what we have here, right? So we got that case. So we used to do this for lab too. So if I have a speed V0, that's how far out it lands, if it takes 10 seconds. So let's do another example related to this. And, all right, we have V0, say 10 meters per second, and it's at a height of, say, 100 meters, all right? Shoot it out. How far out does it actually land? This is Y and that's X. All right, how far out does it actually land? Here, all right, Y is 100 meters. So we'll take this to be 0. Here, why not? Okay. So where does it land? That's a good question. To be able to find X, we have V0, but we need to find the time. So how do we find the time? Well, we find that for how long it takes. Y is given by Y0 plus V0 t plus 1/2 GT squared. All right. So in this case, Y0 is 100. Y is 0, right? So this is Y0, it's launched up here, and Y0 is, it's not. So Y0 is 100 meters. V0 is 0 plus minus 5t squared, okay? So that would mean minus 100. We add it to the other side. We end up with 5t squared equals 100. Divide both sides by 5, so it's t squared is 20. T then is approximately 4.5 seconds. Okay. And then what's X going to be? X will then be 10 times 4.5, which would be about 45 meters. So that's the example there. We're given the height and we're given the initial velocity, and from that we can figure out how far it falls relative to there. All right? If I was to just drop it from here, it would take 4.5 seconds. But given its speed, it still takes 4.5 seconds. So that's one example there where I'm giving initial velocity and the height, all right? Let's do one more example, and that'll be it for chapter 3A. Okay, leave that up for a minute. All right, so let's do one more example. We'll keep our 100 meters, all right? We'll keep our problem here. But what we're going to have, we know it was 45 meters, but let's say it falls at, goes at, well, heck with it. Let's make it 100 meters. So it lands 100 meters away. So it falls 100 meters, lands 100 meters away. Question is, how fast was it actually going? We actually used to do this for lab. Not on the scale, but we do lab on a much smaller scale. Well, let's do an example like that. So we would do it, we would launch it from a tabletop. So y is 1 meter, all right? So y naught is 1 meter, and we would measure it, and x turned out to be approximately, say, 3 meters. So we'd actually do it. So we're trying to actually measure the speed of these things, projectile motion. So we launch and we go out, fall 1 meter, and land 3 meters away. So you could actually launch a projectile horizontally, and it would fall. From that, we could actually figure out how fast it was going initially. So we would do that for a lab problem. All right, you could actually do it by video analysis, which we have since done. So this is what we have. So x is 3, and y naught is 1 meter. Okay, again, we need to find relationship between x. So we want to find v naught, or v naught is x over t. So we need to find t. We already have the 3 meters, but we need to find t. So what do we have here? We go back to another thing. Okay, y is y naught plus v naught t in the x direction, in the y direction, plus 1/2 gt squared. So that's 0 is where it ends up, all right? Oh, yeah. This is 1 plus 0 minus 5t squared. So we end up with 5t squared equals 1. So t squared is 0.2. Take the square root of that is about 0.4 squared, 0.45 squared. Right. Yep. So then divide this by 0.45, and we end up with this being approximately 6.2 meters per second. You know, about 15 miles per hour. Using 1 meter per second is 2.24 miles per hour. So that's would be the answer here, approximately. I'm just doing this off the top of my head, but that's about right. About 6.2 meters per second based on that speed. So that's another example here where we're given x. So this, and we're given the height to fall. So this is actually an easier lab to do. Go back, because how do you measure the speed it's going without some sort of camera or some sort of sensor that can actually measure the speed, or radar detector? Here we could actually do it and find the speed based on these parameters. So that's a bit on chapter 3 as far as